Hello, everyone. My name is Vinit Sehgal. I'm an assistant professor at Louisiana State University. Today, I'm going to talk about something slightly different from what we have discussed so far. I'm going to talk about remote sensing dataset. So I'm going to talk about what are the preferential hydrologic states in terrestrial water energy coupling. So on the surface, this might look like something that is more relevant to atmospheric sciences or hydrology, but I want to talk about how this kind of research is very much relevant to in situ soil moisture sensing and how this can help us derive more information, better understanding of what processes we are dealing with. So we have talked about how we can rely on standardized anomalies in the previous discussion. But what happens if you do not have that long of a time series of data set? You just have a few years of information, or you're setting up a new network, which was just put in last year or last year or two. So we had a similar issue when we were using satellite soil moisture coming in from SMAP to understand drought dynamics and soil hydrologic regimes from the perspective of satellite soil moisture, which was just launched just a few years ago. We just barely had 3 to 4 years of data set. So we had to find a way to understand the soil hydrologic processes from that short, relatively short amount of data set, and how we come up with this particular method of understanding soil hydrology with more focus and emphasis on soil hydrology and soil hydraulic processes. So we are very much familiar with the time series representation of the soil moisture, right? So we know that there's some coupled processes where we have precipitation making the soil wet, and then we have moisture being lost through evapotranspiration. And we are very well aware and very well familiar with the temporal dynamics to see them through a time series of data set. But what if we want to see this data set in a more probabilistic domain? Because now we want to understand what is the probability of the soil hydrology or soil hydrologic state to be in a particular, either that can be in the wet regime or that can be in the dry regime. So what is the probability associated with that? So if I were to ask a question, a hypothetical question, that if I have a time series of soil moisture, and this is just a representation, a schematic, what can be the ideal probability distribution of soil moisture? Can that be a normal distribution? Is that a uniform distribution or an exponential distribution, something like on the bottom? So common intuition says that this density distribution should have the signatures of all those coupled feedback processes that we are going to see at large spatial scale, specifically at landscape scale. So when I say landscape, I mean anything that's bigger than a few hundred feet or a few hundred meters. So at that landscape scale, we have these coupled processes: precipitation, soil moisture, an interaction of vegetation with atmosphere. So how those processes are going to reflect in this probability density distribution, and what kind of inferences we can make out of that. So these are some probability density distributions from some sample location that I'm showing from a SMAP dataset. On x-axis, we have soil moisture, y-axis is density distribution. So we see that the density distributions are skewed. They may be bimodal. So now the question is, why are they skewed? Why are they bimodal? And this all boils down to the discussion that I was having, that all those coupled processes, land atmospheric coupling, coupling between vegetation and atmosphere, coupling between soil and atmosphere, all of those processes go into shaping these density distributions. So now let's look at what we want to extract out of these density distributions. So we are talking about a very generic feedback process of soil moisture. And so we have a water limited regime on the left hand side when the soil is dry. On the right hand side, the soil is wet. So when we get precipitation, obviously the soil gets wet and we lose moisture through evapotranspiration. But there's something that happens in the middle. So we see that there's a line, a vertical line that says hydrologic tipping. So that hydrologic tipping is when you say, in terms of probability, so probabilistically speaking, you say that now the soil has tipped from an energy limited regime to a water limited regime. So from soil hydrological perspective or agricultural sciences perspective, this tipping is important because I'm not just interested in what is the value of soil moisture. Say, if I give you a value of a volumetric soil moisture of 0.35, what does that mean to you? That may mean different based on where you stand based on what your climate for that location is. So that 0.35 doesn't mean anything to me unless I can associate that with a specific regime of water and energy coupling that is visible for that landscape. So I need to find out when exactly that tipping happens, when my soil has gone from energy limited to water limited, basically the point where um, the soil now is the dominant control over variability in evapotranspiration, or now the plants have actually started feeling the stress of drought. So this is the threshold that gives me that hydrologic tipping when the soil goes from energy limited to water limited. And in this study, this is what we are coming up with. So when you don't have very large amount of data set, very long-term observations, how can you still come to a conclusion and understanding of these very critical hydrologic processes with the time series that you have at hand? So this was a study that was done in 2020. The study looked into an emergent signature of soil moisture dynamics. So the series that you see on the right hand side, bottom right hand side, is a typical theoretical soil moisture dry down curve. So on the y-axis, you have rate of loss of soil moisture. So obviously in the gravity drainage, the soil dries faster. Then you get to the wet regime where the soil is able to compensate for potential ET. And then we get into the transitional and dry regime where now we are in the moisture limited regime, stage 2 ET. And the thresholds that you're seeing at the bottom, theta, GW, WT, and TD. So those are the critical thresholds which determine the tipping from one regime to another. So if I were to find out what is this threshold theta GW in terms of a traditional soil hydrology, that is the field capacity. Then we move on to critical point. Then we move on to the wilting point. So now we are trying to understand if we don't have a very accurate soil textural class information, or if the soil texture, because it varies so much from one point to another, just a few meters away, if you are getting in information for a specific location, can you identify these critical thresholds, which is equivalent to wilting point, critical point, and field capacity for the location you are measuring the data? And the best part is that you can just do this with the time series of information that you're seeing at your location. So once we have a volumetric soil moisture time series, we identify the dry down part, which is highlighted in red. And that is the loss, which is because of drainage, because of evapotranspiration. And we just try to understand how that rate of loss for soil moisture is related to the hydrologic state of soil moisture, which is given on the x-axis. So this gave us a lot of good information. In fact, this turned out to be the foundation of a near real-time global flash drought monitor, which is called Flash. We haven't shown it over here, but I'll be very happy to give you that information. And that gave us a very reliable information of emergent flash drought conditions across the globe using satellite soil moisture from SMAP. But obviously, I'm here standing talking about a few more things, talking about how we can get more insights into the process understanding. So that dry down curve had a lot of information. It had a lot of critical thresholds. But we know that there's also a probabilistic likelihood associated with soil hydrologic state. What I mean by that is you may have a fixed value of critical point. You may have fixed value of wilting point. But how much time is the soil spending in that specific hydrologic regime will determine what kind of ecosystem forms around it and how that particular patch of land is interacting with the atmosphere. So not just these critical thresholds, but the likelihood of soil around these critical threshold is what gives you a complete picture of soil hydrology and its interaction with plants and its interaction with atmosphere. So now the idea was how can we go from just the dry down curves all the way to the dry down curves along with the probability attached with these hydrologic regimes. So just quickly browsing through what kind of analysis we did. So we were trying to see what kind of distribution functions are fitting to soil moisture density distribution. A lot of distributions were tested and we found that the truncated gamma mixture density distribution is the best fit for a bimodal density distribution. In many cases, we saw that the density distribution of soil moisture can be bimodal. And for unimodal, we saw that the truncated gamma models were best fitting. We did some AIC-based test and tried to see whether these modes are adequately separated. So based on that, we came up with this understanding of how we can classify soil hydrology based on the preferential state. So if the soil is spending more time in the dry regime where soil moisture exerts limiting control on ET, there's strong land atmospheric coupling. So that state is dry preferential. You are more likely to see that in arid or semi-arid regions. So wet preferential state is where we have more likelihood of soil to sustain energy limited conditions. So you see that the gravity drainage and evapotranspiration very close to potential rates is the dominant factor of loss of soil moisture at that state. And the bistable is a very interesting category because bistable happens somewhere in the middle domain. So it's neither too wet, neither too dry, but there's a lot of good feedback happening. So when the soil gets wet, the moisture is lost. There's a lot of precipitation recycling. The moisture comes back and the cycle repeats. So you see very two distinct modes of density distribution of soil moisture, and you have a very dynamic shift in soil moisture states. There's very strong soil moisture precipitation feedback, and there's either availability of both moisture and energy, especially talking at mesoscale, um, uh, at landscape scale. So these are the examples coming in from very contrasting climates. So as I said, that we were looking into how and what the thresholds of soil hydrologic regimes are. But as you can see, in the humid region, you see in winter, we see a flat line. That means that the soil hydrology for that region, for that season, is predominantly wet preferential. In the dry region in arid climate that's very close to Southern California, we see that the soil hydrology is very it's favoring dry preferential state. But you also see that there are hints of bimodality there as well. That happens because there's a very short amount of time where you get precipitation, the soil moisture gets over to the other extreme, but soon it comes back and stays in the region which is very close to the wilting point, and that is why you see that very dominant peak, and that dominant peak happens close to the wilting point. So we had measured based on these blue curves, those were the dry down curves. So we already had those critical thresholds, but when we overlaid that with the density distribution, we saw that these density distributions occur very closely to the critical thresholds of soil hydrology that we measured from the method I previously discussed. So this is slightly different than what we have discussed so far, but just to give you an idea of how soil hydrologic regimes or preferential hydrologic states vary across the globe, across different seasons. So we see that eastern US in several seasons, especially in the winter, is predominantly in the wet preferential state. Obviously, the dry regions, Southern California, Baja Desert, Sonora Desert, those regions, especially also Australia, large part of Australia is in dry preferential state. So in those part of the world, we are not seeing the soil transitioning too much or venturing too much into the wet state, but stays and holds on to the dry side of the spectrum, and that dictates the ecosystem that builds around that region. I think I've already mentioned this. All right, and now to start with some of the lessons for in situ measurements. So this is just to map where exactly are the modes, because modes of the density distribution give us the place of maximum likelihood for that soil moisture, right? So now we're trying to see if we have two density distributions, which is a bimodal density distribution of soil moisture. Where are those very distinct modes occurring? Where do they actually show up in the spectrum from field capacity, critical point to wilting point? So what we see over here for the dry mode, we see that the dry mode happens very close to the transitional and dry regime. So you will see the biggest mode happening around in this part. Oh, it doesn't show up. Ah, yeah, in this part. So this is where you'll see the biggest likelihood. And this is based on the global metadata that we were observing. But most interestingly, when we look at there has to be a transition coming in from gravity drainage and then wet to transitional regime, right? So where does the soil stay most of the time? And that stays not at the field capacity, but at the critical point. So that happens at the intersection of wet and transitional regimes. So now what we see from a traditional soil physics understanding, we are very interested in field capacity, but what we have seen from the satellite data set, in fact, the critical point is the place which is more better observable, it's where the soil spends more time than actually in the field capacity side of the story. So when you look at this data set, how I kept on mentioning how the soil preferential states dictate the ecosystem around it. So on the bottom left-hand side, we see soil climate regimes based on all the legacy data that we have out there. And on the right-hand side, we see the RGB color composite of 3 tipping characteristics. So I mentioned that there's a tipping point, and then we see what is the intensity, duration, and frequency of hydrologic tipping across that point. And we see that when we map it across the globe, the hydrologic tipping characteristics of soil moisture follow very well the general biomes that we see across the world. And why does that happen? Is because when we study the intensity, duration, and frequency of these hydrologic tippings, they have a very unique relationship with plant functional type, climate, and soil texture. And when you overlap these 3 information, you get a very unique coexistence of plant, climate, and soil texture, which for us becomes the foundation of an ecosystem. So that is why these hydrologic regimes and tipping characteristics have so much information about ecology. So we also have ecohydrological linkages more clearly defined over here, because if we see, we have plant water stress threshold as we go from wet to dry, that threshold decreases. And as we go from dry to wet, the land atmospheric coupling strength actually decreases, because now soil is not as dominant a contributor to the ET temporal dynamics. And we did a small analysis to highlight how these tipping characteristics are actually able to discretize or separate out different ecosystem within each biome. And we saw that compared to the mean soil moisture, the tipping characteristics were in fact a better contributor or better predictor of separation between different biomes. So just a few applications where we are headed with this. We toyed around with a few ideas of, because now we are saying that we have these tipping characteristics which are very closely related with soil hydraulics, ecosystem dynamics, land atmospheric interactions. So we were trying with the idea, can we make watershed scale ecoregions which can become the discretized units equivalent to what we have of HRUs in SWOT models, or typical soil hydrology, or typical water balance models in hydrology. We were also seeing if we can see the shift in the ecosystem because of climate change. So if we have a grassland converted into a cropland, or it dries out and there's land degradation, can we track this movement just with the help of these tipping characteristics and differences in these soil hydrologic regimes? And also because each of these tipping characteristics are influenced by very uniquely by soil texture or climatic forcings, these can be very critical elements of diagnosing Earth system and climate system model to see where exactly is the uncertainty in those models coming in. So to conclude, these preferential state capture the temporal sustenance of the dominant hydrologic regimes, and be classified into wet, dry, and bistable states. More importantly, to conclude, if we are working with soil moisture data set, the representation of the temporal dynamics cannot be stated with the mean soil moisture that we are very used to. Because in the case of bistable or bimodal density distributions, that value of the mean soil moisture may actually not hold a lot of probability attached to it. So understanding this dynamics of soil moisture in time as well as in state is very important to completely understand the physical processes governing them. So that's pretty much it. Thank you so much.
We have time for one question. I'll give you one question, if there is one. If not,
Just slide 5, wondering what the scale of time was on the chart.
slide 5. What is the scale on the chart?
Now we're converting the data from time scale, that is the time series, to a state series. So now we are crunching the numbers. So this data, it can be 2 years, 3 years, 4 years, but it will all boil down to that. So now there's no time scale associated with this curve. That is the beauty, because now no matter how long your time series, if you have short-term time series, if you have very long-term time series, you can still generate that kind of information and go with that. And that's very important if you are trying to convert this information to, say, an understanding of how the soil are stressed, or what kind of drought impacts you're seeing in your region when you don't have too long of a time series. Thank you.
Thank you, Vinit.